Hello, I'm Neil, Chair of the Patient-Centric Sampling Interest Group, and I'd like to welcome you to our latest webinar, Evidence versus Adoption in PKU Monitoring, Understanding the Implementation Gap. And I'm really excited that we've got Rachel Carling from Synnovis today speaking to us. But before I hand over to Rachel, just got a couple of housekeeping slides to get through. So first of all, just like to thank the sponsors for the Patient-Centric Sampling Interest Group, without whom we wouldn't be able to bring you these webinars for free. And just remind you that all the webinars are available on our YouTube site as well and through our website. So thank you to all the sponsors who enable us to do this and the other activities that we have in the Patient-Centric Sampling Interest Group. Just a reminder to everyone, hopefully we'll have plenty of time at the end for questions. Please use the chat function, and the webinar is being recorded and will be available probably early next week for you to be able to view through our website and our YouTube channel. So no further ado, I'll hand over to Rachel. Thank you, Rachel.
Thanks, Neil. Good afternoon, everyone, and thank you for joining today's webinar. So as Neil said, my name is Rachel Carling, and I'm a consultant clinical scientist at Synnovis, and we're the pathology providers for Guy's, St Thomas's and King's hospitals in London. So I'd like to talk to you today about something that's occupied a significant amount of my working life over the last few years, and that's the biochemical monitoring of patients with phenylketonuria, and specifically why improving this has turned out to be considerably harder than the science indicated it should be. So just start with a quick overview of what we're going to cover today. I'm going to start by reminding you all what phenylketonuria is and how we currently monitor patients with PKU. And then we'll talk about some of the problems we're having with PKU at the moment, before talking on about what we're going to do to try and address these issues, and probably most importantly, what progress has been made to date. So then for the second half of the talk, I'll focus on the implementation gap and the challenges that we're experiencing with changing current practice. And then most importantly, I'd like to talk about strategies we might be able to use to help navigate these. So what is PKU and why is monitoring of it important? So PKU is caused by mutations in the gene encoding phenylalanine hydroxylase. So this is the enzyme that converts phenylalanine into tyrosine. When you have a deficiency of that enzyme, phenylalanine accumulates in the blood, and this is neurotoxic. So if PKU is left untreated, it causes severe and irreversible intellectual disability, seizures and behavioural problems. It's actually a really nasty disease and there is no cure for it. However, PKU is one of the great success stories of newborn screening. If we can identify these babies in the first few weeks of life and restrict their dietary phenylalanine intake, they can lead essentially normal lives. So the photo of the two children you can see here is a classic photo that's often used to illustrate the benefits of newborn screening. So these two children are siblings. The boy on the left has PKU and he was born before newborn screening was in place. His younger sister is on the right and she was identified at birth and immediately placed on a phenylalanine restricted diet, and she went on to lead a normal life. So newborn screening for PKU has been in place in the UK since the late 1960s, and it's offered to all babies who were born in the UK. Blood's collected from a heel prick sample onto a filter paper collection device. This is often just called a newborn screening card or a Guthrie card, and then it's tested for phenylalanine. So while we can't cure PKU, we can effectively treat it with a low phenylalanine diet. Now this diet is very restrictive and it requires lifelong compliance. In addition to restricting the intake of dietary protein, these patients need to be given phenylalanine-free protein substitutes because obviously protein is required for normal growth and development, and this is particularly important in babies and children. So patients are managed in line with the European guidelines, and these were first implemented, I think, in 2017, but they were revised last year. And these guidelines define target treatment ranges for blood phenylalanine. So for children, the target range is between 120 and 360 micromoles per litre. And there's a little bit more flexibility with adults going up to 600 micromoles per litre. And to help manage these diets effectively, we monitor blood phenylalanine levels regularly. So in the first year of life, this is done weekly. It's done fortnightly in children and then monthly after the age of 12, assuming that the patient is relatively stable. And probably the one exception to this is pregnant women, and they require very close monitoring because phenylalanine is teratogenic to the developing fetus. So more recently, pharmacological options have become available to treat PKU. So sapropterin is a synthetic form of tetrahydrobiopterin, and this is the natural cofactor for phenylalanine hydroxylase. And sapropterin can be used in those patients who are responsive to it, and approximately, I think, 1 in 4 will be. There's also a treatment called pegvaliase, which is an enzyme substitution therapy, which has been approved for adults with poorly controlled PKU, but this isn't currently available on the NHS. So the 2025 European guidelines define targets for responsiveness to sapropterin. And initially, this is defined as a reduction in blood phenylalanine of 30% or more following a loading test. And then long-term responsiveness to the drug is defined as having 75% or more of your blood phenylalanine results falling within the target range. So effectively, this is the endpoint that determines whether a patient continues to take this drug or not. So as we go through the talk, I want you to try and hold these numbers in your mind. So we've got 120, 360, and 600. So those are the key clinical decision points. And then we've got the requirement of the 30% reduction, and then 3/4 of all results being within the therapeutic range. And that's to demonstrate the responsiveness. So before I get into some of the challenges related to monitoring this group of patients, I just want to talk through the process of how things work at the moment, because I think it will give some important context for the rest of the talk. So a patient with PKU collects a capillary blood sample at home. They prick their finger with a lancet and apply drops of blood onto a filter paper collection device. So this is a standard newborn screening card, which sometimes gets referred to as a Guthrie card. And that's because Robert Guthrie invented the Guthrie bacterial inhibition test, which was the original PKU screening method. So the blood is allowed to dry on the card at room temperature, and then the card is put into a special envelope and posted to the metabolic biochemistry lab, either by first-class post or recorded delivery. And in my lab, we analyse and report all samples on the day of receipt. And that's pretty much standard practice for most labs in the UK. Now, the results don't go directly to the patient. They go to the metabolic dietitian who interprets them and then advises the patient if any dietary changes are required. And as with most monitoring tests, a single result in isolation has limited value. And what you normally do is you look at the trend of results in relation to how the patient's doing clinically. And this is much more informative. PKU monitoring is pretty much the bread and butter test of a metabolic biochemistry lab. So in 2021, there was approximately 2,100 patients in England with PKU, and the combined annual workload was just over 60,000 dry blood spot samples each year, which isn't insignificant. I just want to say a brief word about postage as well. The cost of a first-class stamp is now £1.70 and recorded delivery is £3.25. So a patient who's monitoring themselves weekly is going to be spending between £90 and £170 a year on postage. And interestingly, depending what region that patient lives in, they may have to pay for this out of their own pocket. I think it's fair to say that newborn screening is probably the best established example of microsampling that there is. But newborn screening samples are collected by healthcare professionals, and that's the difference. So with PKU monitoring, I think this must be the best established example of microsampling, where the patients are actually collecting the samples themselves. And that's an important point to acknowledge, because it explains why today's talk is probably a bit different from your normal microsampling talk. Volumetric blood collection devices are typically described as transforming patient pathways across many different areas of medicine. And this narrative is consistent, and it's also really quite compelling. The patients who previously have had to travel to a clinic or to a hospital for blood samples can instead collect a capillary blood sample at home, post it to the lab, and receive their results without even having to leave the house. And for patients on therapeutic drugs that require regular monitoring, people living with chronic disease, people who live in remote and rural areas, and those who struggle with mobility, this can be really beneficial. And obviously, has other advantages as well. It also reduces the cost of phlebotomy, the burden on clinics, and it minimises unnecessary travel. But PKU monitoring is a different story. Patients with PKU have been collecting their blood at home for more than 30 years using a finger prick sample and a newborn screening card. So microsampling is not an innovation here. It's just the long-standing, well-established status quo. And because the patient pathway is already using remote monitoring. So what we're trying to achieve is something slightly more subtle. What we would like to do is replace that traditional newborn screening card with a more sophisticated sample collection device. And the reason we want to do this is because we want to improve the quality of the dried blood spot sample that's being used to monitor these patients. And I'm going to go on to tell you why I think this is so important and what we have done to date to try to improve the current system. I'm also going to talk about what we have yet to achieve, but in a nutshell, I hope that will be implementing a volumetric blood collection device into routine practice for monitoring PKU patients. So the problems, let's talk a little bit about this. And again, I think probably the best place to start is actually with the method, because that's essentially how this whole story started. Dry blood spot phenylalanine is measured by flow injection analysis tandem mass spectrometry. So this method was developed in the early 1990s for newborn screening, and it was genuinely revolutionary at the time. So it enabled multiple analytes to be measured simultaneously on a single drop of blood with a throughput of around 1.5 minutes per sample. So it was a complete game changer for newborn screening. For programs who were processing hundreds of thousands of samples each year, it transformed what they were able to do. And because the method was being used in newborn screening labs every day, it was a relatively logical step to say, let's use the same method to monitor these patients with PKU. And why wouldn't you? And I think 30 years ago, that probably was an entirely reasonable thing to do. But the problem I think is that the method has barely changed since. But technology has changed. So mass specs can scan faster, they're more sensitive. We have ultra performance liquid chromatography now, which means that we can have chromatographic separation and we can achieve it without any meaningful increase in analysis time. So liquid chromatography tandem mass spectrometry would offer superior selectivity over the current flow injection analysis method because it enables separation of these isobaric interferences. But when we surveyed UK labs in November last year, 15 out of 16 were still using the legacy newborn screening methods to monitor PKU patients. So it feels a bit like this method is frozen in time. And I think this is a fundamental issue that I don't think is widely appreciated outside of the laboratory. But the performance criteria for screening tests are very different to those for monitoring tests. With newborn screening, it's essentially a binary test. You want to know if the baby's phenylalanine is above or below the referral threshold. So you need adequate sensitivity and specificity, but you don't need the kind of precision that allows you to track subtle changes over time. And the other thing about newborn screening, of course, is that positive results are always confirmed by a different method. Whereas with monitoring, it's a different kind of analytical challenge. We're trying to detect whether the patient's dietary therapy is well controlled, so whether they are within the therapeutic range or whether they're starting to drift out of control. And now in some cases, this monitoring test is also used to determine whether patients are responding to drugs such as sapropterin. So if you remember, I said there was a 30% reduction after a phenylalanine loading test, and then 3/4 of results being within the therapeutic range. So for monitoring, we need a method that is precise, that's accurate, and it's across the concentration range. And importantly, that's also comparable between labs. Yet we are trying to do this with a method that was designed for newborn screening 30 odd years ago, and which is based on a crude single point calibration. So I think probably a good way to try and describe the impact that this has on PKU monitoring is to talk about uncertainty of measurement that's associated with the monitoring method. And I think this is underappreciated, not just by clinicians, but I do think sometimes within the lab community itself. So the estimated uncertainty of measurement for dried blood spot phenylalanine in my lab, based on intermediate imprecision data, is plus or minus 12%. I don't think that sounds unreasonable, but there are two things that you need to know about this figure. First thing is it was derived from IQC material. So that means it was based on repeated measurements of an ideal dried blood spot material, which had been prepared in the lab by pipetting a fixed volume of blood onto a piece of filter paper. So it's not representative of the variable patient-collected specimens that make up our routine workload. We'll come back to that shortly. The other thing to know is that this type of estimate doesn't take bias into account. So it's actually underestimating the uncertainty of the measurement. And the reason that we haven't taken bias into account here is because there's no commercially available matrix match certified reference material for dried blood spot phenylalanine. So what we do to try and factor in bias is look at external quality assessment data, and we use the Earned-In Special Assays in Dried Blood Spot scheme. So the Earned-In scheme shows us that mean intra-laboratory imprecision is about 10%, whereas the mean inter-laboratory variation exceeds 20%. So what this is indicating is that whilst labs have similar imprecision, accuracy is more of an issue. So labs are neither harmonized or standardized. Another important point to make is that the Earned-In EQA scheme reports results relative to the all laboratory trimmed mean, not the true or assigned value. So Earned-In results are really only telling us about harmonization. They're not telling us anything about standardization. And this means that a lab can appear to be performing well in the EQA scheme, but they could actually have a systematic bias, which wouldn't be evident provided the majority of labs also had a similar bias. So it's not a meaningful measure of accuracy. And because we don't have access to these matrix matched reference materials, we have to rely on in-house calibrators, but we have no external point of reference to check them against. So our in-house calibrators, if I'm honest, often leave a lot to be desired. And on top of that, preparing dried blood spot calibrators is notoriously difficult to do well. So many labs choose to quantify patient results using isotope dilution alone, even though the limitations of this approach are well known. And in practice, this means that if two labs are to analyze the same patient sample, the reported phenylalanine results could differ by around 30%. So in other words, a sample with a nominal concentration of 360 micromoles per litre at one of our key clinical decision points might be reported as anything between 244 and 475 micromoles per litre. All right, so obviously I've chosen a worst case scenario example, and we do look at the trend in a patient results. That's always taken into account before a dietary change is implemented. So this practice isn't quite as bad as it sounds, but I do think most of you, I hope, will agree that that level of analytical performance is not really ideal. And then again, just to go back to that 30% reduction of phenylalanine, which is being used to determine whether a patient's responsive to sapropterin. But, and this is a really big but, this possible 30% error there is a possible 30% error before we factor in the quality of the dried blood spot samples themselves. So the imprecision of 12% that I talked about earlier is based on a dried blood spot that we prepared in the lab by pipetting out a fixed volume of blood onto filter paper. So it's an ideal sample, and it's very different from a dried blood spot sample that's collected by a patient. So the application of blood from a finger prick to a filter paper card is not volumetric. The patient applies a drop of blood into a circle on the card, and the assumption is made that a 3.2 millimeter punch of that spot will contain a defined and consistent volume of blood. But that assumption will only hold true if the spot is of an adequate size, if it's formed from a single hanging drop of blood, and if it completely soaks through the filter paper. And in practice, what we see with patient-collected specimens is that they vary quite significantly. And the hematocrit of the blood can also have an effect. So the evidence of what this does to the measured result is now very well stated. It's completely unambiguous. A spot that's smaller than 8 millimeters in diameter can bias a phenylalanine result by up to 20%, so negative bias, compared with a good quality specimen. A compressed spot, and this is what happens if a patient handles or transports the card before it's fully dried, or if the spot, for whatever reason, is pressed to try to fill the circle, results from these samples can actually be 35% lower. And multi-load specimens, where a patient applies multiple drops on top of each other, obviously give results with a positive bias. And then the location that the punch is taken from can be a factor too. So a sub punch that's taken from the center of the spot compared with one that's taken from the edge can give different results. And that's because blood doesn't distribute evenly across the filter paper. So data on this slide is from a paper published in Clinical Chemistry about 10 years ago by George and Mote. And it shows data from a single patient with PKU, so that their blood was applied at different volumes and punched in different locations. And the results range from 930 to effectively 1300 micromoles per litre. So that is a range of 368 micromoles per litre from a single sample, just because of the quality of the spot that the lab analysed. And what's really important about this, the biases that are associated with blood spot quality, is that this is pre-analytical variability. So this happens to the sample before it's even reached the lab. And because that is the case, it's not factored into a lab's estimates of measurement uncertainty or total analytical error. So analytical variation can bias results by 30%, but so can pre-analytical. So on a good day, they might cancel each other out. And on a bad day, you could end up with a very misleading phenylalanine result. But obviously, as we all know, it's a UCAS requirement that labs don't report results on samples they know are unsuitable. That's also common sense, to be fair. But historically, these patient-collected samples have been considered special, and there has been a reluctance to reject them. However, now that we know what the impact of sample quality is on a dry blood spot phenylalanine result, this approach is obviously no longer acceptable. And in 2015, the newborn screening programme implemented formal blood spot acceptance criteria for newborn screening labs. And although the UK Metabolic Biochemistry Network has adapted those criteria for monitoring samples and made the recommendation to labs that they're implemented, embedding this change has proved to be really challenging. So Sarah Hogg did a retrospective audit across 10 metabolic labs in 2022, and she reviewed over 2,000 dry blood spot samples that had been received for phenylalanine monitoring from more than 1,000 different patients. And she assessed each specimen against two sets of criteria. So the first was that lab's existing acceptance policy, assuming one existed. And then the second was the formal newborn screening criteria. And the results were quite striking. Using current local practice, there was a median rejection rate of 4%, which sounds relatively manageable, but there was a lot of variation between labs. And one lab didn't actually have any rejection criteria at all. And when we looked at the rejection criteria using the evidence-based guidelines, the median rejection rate increased to 22%, and it ranged from 10 to 33% across the 10 labs. And the most common reason for rejection, out of which I think accounted for 70% of all samples that were rejected, was that the specimens were too small for analysis or that they were multi-spotted. So these audit findings were extrapolated to an annual workload of 62,000, and that equates to just short of 12,500 patient results being reported inaccurately every year. And these results are used to inform dietary management decisions. So labs are in a difficult position. UCAS guidance makes it clear that we have an obligation to reject samples if they're unsuitable for analysis. But we don't want to reject 22% of samples. It would be clinically and operationally unworkable. The clinical teams would be up in arms, and it would probably impact negatively on quite a few patients who were trying really hard to collect good samples. And obviously patient education and retraining helps, of course it does, but experience shows that this does take time and effort. And importantly, it also needs to be ongoing and targeted if it's going to be effective. So what we could do is a solution that makes it possible for patients to collect good quality samples every time. So in other words, we might need a volumetric blood collection device. But we also need to solve our analytical issues. So essentially we have three different things that we need to consider. We have the pre-analytical issue to improve the sample collection device, and then we have two analytical issues. We need to improve that legacy method, and we also need to standardize the method. So this slide shows a study that was done in 2023 looking at interlaboratory variation of dried blood spot phenylalanine in the UK. And the reason we did this is because we wanted to baseline the current analytical performance of dried blood spot phenylalanine. So we wanted to know actually what was happening in practice as opposed to estimates of uncertainty and error from our IQC samples. So this was done using a lab-prepared dried blood spot with a nominal concentration of 360 micromoles, which was sent to all 17 UK labs. And they analysed this sample in triplicate on 3 different days. And these box whisker plots represent each of the labs, and you can see or get a feel for the intra and inter laboratory variation. And the mean measured result of this sample varied from 230 to 425 micromoles per litre. And so basically this experimentally confirmed the estimated total error that we talked about earlier, and just reinforced that we do need to address harmonisation and standardisation. So we took 2 approaches to improving standardisation. First of all, we reviewed our legacy dried blood spot phenylalanine method. So this was a collaborative project that involved Bristol, London, Queen Square, Cardiff, and Synnovis, as well as LGC, who very kindly value assigned 4 dried blood spot materials for us to use in this study. So first of all, we optimised the sample extraction process, and then we introduced a chromatographic separation step in the method. So this improved the recovery of phenylalanine from the dried blood spots and also the selectivity of the measurement. So it wasn't anything very cutting edge, but I think it was quite effective. We validated this at Synnovis first, and then we shared this method with the other 4 labs. And we also sent them a common aqueous calibrant. So this was a certified reference material traceable to SI units. And we asked each lab to look at 3 different calibration approaches. And this is what the 3 graphs represent on this slide. So we looked at internal calibration. So this is isotope dilution alone as used in the newborn screening method. And then we looked at multi-point aqueous calibrations. So in the middle graph, the aqueous calibrations were prepared by each individual lab and sourced independently, although all choosing the same product. And then the third graph shows the centrally distributed calibration curve. And I think the results were really encouraging. You can see straight away that the interlaboratory coefficient of variation for phenylalanine reduced significantly. So it was actually reduced 8-fold simply by moving to a common method and a common calibrant. So we were quite happy with that. But obviously in parallel to this, we've been looking at volumetric sample collection devices and comparing their performance to that of our traditional newborn screening card. So this work was published in 2022 in Clinicians Acta, and we evaluated the measurement of phenylalanine using the Capitana QDBS device, the Himaxis DB10, and the Neoterix Mitra. And the Neoterix was a slightly different device because it uses volumetric absorptive microsampling technology rather than filter paper. And we looked at 4 parameters for each device. So we looked at the effect of blood volume on the measured result, the effect of hematocrit, imprecision and accuracy. And we measured accuracy relative to liquid blood. And then importantly, we assessed each device for its practical compatibility with the existing workflows in a metabolic lab, because a device that performs beautifully in a research setting but can't be integrated into routine practice isn't going to be a solution for us. So I didn't want to spend too long on the analytical findings. I think it's probably enough to say that our conventional newborn screening card had by far the worst performance, and it showed a significant systematic bias when compared to liquid blood. And of course, this is a device that we currently use to monitor patients with PKU. We found that the analytical performance of the Himaxis and the Capitana devices were really good. They were precise, they were accurate, and they were unaffected by the hematocrit. But in the end, our preference was for the Capitana QDBS device because it was directly comparable with our existing workflows, and the Hymaxis one wasn't. So what we did next with the Capitainer was to use it to compare plasma phenylalanine measurements with dried blood spot collected volumetrically. And then we used, for both sample types, we used the same method. So this was the new LCMS method to perform the comparison. This was a formal service evaluation that was done between London, Bristol, Cardiff and Cambridge. And we recruited 51 patients with PKU and collected paired plasma and Capitainer dried blood spots from them all. And the results are summarized on the slide here. So you can see that the correlation between the plasma and the dried blood spot was excellent. R squared was 0.992. And then you can see that the regression confirmed a proportional relationship with no significant systematic error and a mean bias of 13%. And this was interesting because we know that a bias of 13% is approximately consistent with the under-recovery of phenylalanine reported from filter paper, which is 11%. So I think that probably indicates that if you allow for experimental error, there probably isn't any real difference between phenylalanine levels in plasma and blood. And I think that in itself is useful information to know. So this is perhaps the most important assessment for any microsampling device, is to find out what patients think about it. So we went to the National Society of PKU's annual symposium in 2022, and we distributed Capitainer devices and instructions to 44 patients in an attempt to find out what they thought of the device. So we asked these patients to try the device and then complete a questionnaire. 15 of them returned their questionnaires. So we had a response rate of, I guess, about a third, which isn't bad for some kind of opportunistic survey done at a conference. But I want to be quite clear about the limitations of what we did. It was a really small number, and it was a self-selecting group of engaged patients who were present at a national conference. So I'm not trying to claim that this is a definitive patient evaluation study, but I do still think that the data is meaningful because of who responded to it. So 14 out of the 15 were adults, and 71% of this group had been collecting blood spot samples for more than 10 years. So these aren't people who are unfamiliar with dried blood spot collection. They've been doing it for most of their lives. So in some ways, I think they are the ideal comparators. And interestingly, they did seem to prefer the Capitainer to the conventional newborn screening card. They gave it a median score of 10 for overall satisfaction compared to 8 for our traditional newborn screening card. But I think probably maybe the most compelling evidence wasn't so much the numbers, but it was what the patients wrote about the device. So one patient said, "This is so good. It's incredibly simple. I hope it becomes the new normal." Another said, "Much less stress than the standard blood spot cards. Really reassuring to be able to see straight away that the spots are okay." And the third person said, "Fantastic. So much easier to use. Got 2 successful samples straight away. Would much prefer to use this than current forms." So this all sounds really positive. The patients appear ready and willing to use a Capitainer device, which means we can potentially resolve the pre-analytical issues. And the labs have access to a simple, harmonized and standardized methodology, which will go a long way to resolving our analytical issues. So in theory, we should be ready to go. But unfortunately, the work I've talked about today was completed in 2023, and it's now 2026, and we still haven't implemented the Capitainer device or the method changes. So I have to ask, why is that? And I think if I knew the answer, I probably wouldn't be giving this talk today. I have given it a lot of thought though, and I think the first barrier is probably cost, and it's certainly the one that's been flagged consistently as an issue. And it is a barrier because the sample collection device does cost more than the newborn screening card. And I know you're all going to want to know how much more. And it's not that I want to avoid this question, but equally, I don't really want to get into a detailed discussion about the cost of the device, because obviously the cost varies with the volume. So a quote for an individual metabolic lab like mine is going to have a higher unit cost than a nationally coordinated procurement across all English metabolic services might have. But if we say, for argument's sake, that the device costs £5 more than the newborn screening card, we can have a think about what this impact is in terms of cost. So if we assume that an average patient is collecting samples fortnightly, this would equate to an increase per patient of just £10 per month or £120 per year. Sounds great. If we scale this up for the 2,100 PKU patients living in England at the moment, it jumps to about 250,000, which sounds more significant. But then if we compare this to the cost of a low protein diet for PKU, it becomes somehow a lot smaller, because between June 2024 and May 2025, NHS England spent 22 million on metabolic formula specifically for PKU, and they spent a further 2.9 million on low protein foods. So the second barrier, I think, is the absence of a cost benefit analysis to support, or possibly to go the other way, but to look at this case. Because if we don't have the cost benefit analysis, the argument about cost is being made in a vacuum, and people are throwing figures around willy-nilly, a bit like I just did, to be honest, because until this has been properly evaluated, we are just speculating. And I think this is a really important point. And I'm really interested to hear from anyone who's listening today to find out if you are aware of any similar use cases that have been made for other microsampling devices that might be able to provide some guidance or give us a little bit of insight. So I think the third barrier we have is resistance to change. And I'm not saying this to be critical. I think, just being honest, it applies to all of us. The current process of PKU monitoring is familiar. It's been running for 30 years. It's embedded in all clinical, dietetic and lab workflows. It's like the institutional memory of every metabolic service in this country. And the fourth barrier, which I think probably underpins the first three, implementing these devices doesn't appear to be a priority for the clinical teams at the moment. So no one is really driving this change. And what's funny, or perhaps it's not funny, but what's a bit of a paradox is really that our clinicians do care about these patients, and they do care about the PKU results. And I know this because when something goes wrong, if a sample has to be rejected, or results are delayed or reported the next day, or if there is a problem with our assay, the clinical response is immediate, it's urgent, and it's genuine. Our colleagues want to know what's happening with those patient results. But I think what's interesting is that that same urgency isn't applied to preventing some of these problems before they occur. So we have a reactive response when things go wrong, but we don't have any preventive investment. And again, I think this is human nature. And I think possibly, and be interested to see if you agree, I wonder if it's exacerbated by the fact that the issue we're talking about is essentially invisible. So when we report a falsely low result because the blood spot was small, nobody actually knows. The result arrives, it appears to be a feasible result, and a dietary decision is made, and the error remains effectively hidden. So it's only when we're auditing data or looking at EQA results or digging into interlaboratory comparisons that the scale of the problem becomes apparent. And these things tend to be in the remit of the lab. They don't sit with the clinical teams. So the pre-analytical and the analytical problems are largely invisible to our users. And that's why Sarah Hogg's audit was so important. And equally, that's why the sample collection device could be really important. So I have got a recent example of what I've just tried to describe that made me feel a little bit more optimistic. So as you may be aware, in September, October last year, the newborn screening program started screening for tyrosine type 1. And at the same time, the newborn screening program moved to a new kit for newborn screening. And when they moved to this kit, there was a 15% negative bias on phenylalanine results, which the program knew about and were happy with. But 3 English labs are using that newborn screening assay exactly as is to analyse PKU monitoring samples on. So within a very short time frame, I would say about a month, a complaint was made to Met Bionet about the change in PKU monitoring results. The clinicians and dietitians noticed because their patient results had shifted by 15% at the same time. And a 15% systematic bias from a method change was immediately flagged as unacceptable by the clinical teams. But as I've been telling you today, we potentially have pre-analytical bias of up to 35% and analytical bias of another 35%. And that's been present in this monitoring system for decades, and it's generated almost no clinical response. So I've come to the conclusion that the difference isn't the magnitude of the error, the bias, but it's how visible it is. So when an error affects all patients simultaneously, it becomes visible. But with the others, they typically affect one patient at a time. They're random and they get lost in the noise. But the encouraging thing, or the good thing that's come out of this, is that the issue with the newborn screening method change has put method performance of PKU monitoring back on the agenda. So last month, there was a meeting between Met Bionet and BIMDG representatives, and we agreed that labs did need to move to LCMS assays calibrated using the Aquis CRM. And as a result, I was asked to set up a working group, and 9 labs have already volunteered to join this group. So I'm feeling quietly confident that we are going to start to make some progress here. And my hope is that once the analytical standardization piece is in place across all labs, the case for the pre-analytical piece, so the Capitainer device, will be perhaps harder to ignore. And the other thing I think we probably need to do is to reframe the conversation, because I think the current framing hasn't worked. Statements about analytical improvement reduced into laboratory variation and bias are not landing well with our clinical colleagues. And so I've been wondering about the best way that we can do this. And I think that there are a couple of very timely reports that might just help us. So the patient-focused laboratory medicine report was published in February this year. And if you haven't already read it, I would really encourage you to do so. So this report was prepared in response to the HbA1c bias scandal, and it makes some really interesting points about clinical biochemistry, quality, governance, and the gaps in oversight that allowed a systematic bias with HbA1c to go unaddressed for years. And I think that there are some important parallels there with our PKU method that we really need to consider. And interestingly, these points have just been picked up by Rachel Marrington and colleagues, who published a paper in the Annals of Clinical Biochemistry where they asked that question: who is responsible for ensuring clinical chemistry assays are fit for purpose? And to quote Rachel Marrington, as she says in the paper, the problem is that nobody thinks that the problem is theirs. So in conclusion, the monitoring of phenylalanine in patients with PKU currently has 3 problems: sample quality, harmonization, and standardization. All 3 are documented, all 3 are relatively well understood, and all 3 have a solution, potentially anyway. The patients appear happy with the proposed change, but what isn't ready is our system. So we have an information gap. The cost benefit of implementing these collection devices is not known. There's also a priority gap, because in the absence of any immediate visible crisis, the status quo is just quietly persisting. And then there is probably an ownership gap, because no one thinks the problem is theirs. However, that report does very clearly say that labs have a responsibility to make sure the tests they offer are fit for purpose. And I think that has been emphasized very clearly. So I think we need to take ownership of this problem. So we need to implement the optimized methodology, and then we need to work with our clinical colleagues to find the right solution to improve sample quality, and accept that that might not be the Capitainer device, because the main thing is that we do improve sample quality. So thank you all for listening. I hope you found it useful. And I just very quickly like to acknowledge a few people who were involved with several parts of this work. So Erin Emmett and Zoe Barkley from Synnovis, Stuart Moak from Cardiff, Emily, Chris and Chloe from LGC, and then of course the other labs in the metabolic biochemistry network, with a special mention to Cardiff Cambridge, Bristol and Queen Square, who collaborated with us on the study. And then obviously the delegates at the NSPKU conference. So thank you.
Thank you, Rachel. That was a really interesting story. Really, excuse me, really fascinating. And hopefully we are turning the corner, and people realize that if we're going to make measurements, it's worth having measurements that are real and that we can really use the data. So thank you for sharing the story. It's fantastic. So we're starting to get some questions coming in. I'm just going to take them in the order that they came in. So Peter has asked, does time of day matter for sampling? Just curious.
Yeah, I think most patients collect at the same time of day, often in the morning. But I believe some also do it on a Sunday evening. And that's a very good point. I'm glad somebody mentioned time of day, because when we were talking about measurement uncertainty, often in that kind of discussion, we would also talk about biological variation. But in this case, with phenylalanine and the fact that the patients are on such a controlled diet, it's not really something that we use. And I don't even think it's actually that well known in blood spots, although I know there is data on plasma phenylalanine.
Okay. Got a question from Marlene. Have there been any fatal consequences as a result of the phenylalanine measurement variations between labs / countries? Doesn't the UK have something similar to College of American Pathologists, CAP, that ensures laboratory proficiency?
Yeah, so that's another good question. So we do have something similar to, we have the UK NEQAS scheme, it's an EQA scheme, and they provide dried blood spot phenylalanine monitoring results. Unfortunately, like the Herndon scheme I mentioned in the talk, and most if not all UK biochemistry labs participate in both schemes, the results are just reported relative to the all lab trimmed mean. And unfortunately, in the NEQAS scheme in particular, there isn't that many laboratories who participate, so it can very quickly become a circular argument. And there is also a small minority of labs who do confess on occasion that they align their methods to the EQA samples. So, yeah.
Okay, thank you, Rachel. Question from Martina here. Thank you, Rachel, for your great presentation. Just a curiosity, have you tested the stability of phenylalanine and tyrosine in volumetric DBS samples, Capitana? Yeah,
we have, and I think one of the advantages of these kind of devices, the Capitana and the Himaxes, is that the samples they're collecting are essentially, I'm not going to say identical, because I don't know who's on the call, and one filter paper does not necessarily equal another, but essentially these are just collecting dried blood onto a piece of filter paper in the same way that we're doing with the newborn screening card.
Okay, thank you. Balvinda says, is there a method for using venous samples instead to reduce pre-analytical error?
So we haven't looked at that. So that's a very interesting question. My guess is that if we could get a small amount of capillary blood and it could be sent to the lab, there would be probably not a huge reason why we couldn't give it a go, given that we can't. I think we have more chance of getting a dried blood spot sampling device implemented than persuading people to change to capillary blood.
Yeah. Couple of just thank yous. JD says, thank you, Rachel. Really interesting presentation. Daniela says, thanks, Rachel. Question from Chris. Thanks, Rachel. Ownership gap. What does the Chief Scientific Officer England view on this?
I have no idea. I'll have to ask her. I suspect, I'm pretty sure she won't think it's her responsibility. But no, joking aside, I'm not sure. I think ultimately, I think we need to assume it's a lab responsibility until proven otherwise.
And just a question from me, Rachel. Are there any other measurements, analytes out there that could be having this same problem that we've just not looked yet?
Yes, there is. So even or specifically within metabolic, the world of metabolic, we monitor several groups of patients with inherited metabolic diseases who are on dietary therapy. So in my lab, we offer a branched chain amino acid monitoring service. Patients do exactly the same thing as a PKU patients. They collect samples at home, send them to the laboratory in the post, We analyse them same day and report results. We also look at patients with homocystinuria and patients with tyrosinemia. And tyrosinemia is a very interesting example, because at the moment these patients are treated with NTBC, and NTBC is obviously a licensed drug. Essentially, it's a weed killer, so it's a really nasty drug. And these patients are given NTBC to suppress their succinylacetone, and this is monitored on a dried blood spot. So we measure the tyrosine and the succinylacetone and the NTBC, and that, I think, has to be or must constitute therapeutic drug monitoring. And yet we're doing it on these dried blood spot samples. So yeah, I think there is a bigger case that could be made.
Has anyone looked at that yet, Rachel?
I don't think anybody's looked with a Capitana device, but I know it's been discussed. We've talked about it internally, but I think we felt that, rightly or wrongly, we felt that PKU patients would be the place to start, because it's the biggest single group of patients. Tyrosinemia is much less common, so is homocystinuria, and maple syrup, the cohort of patients, is probably somewhere in between.
Yeah. Just also wondered, from an analytical point of view, the switch from flow injection analysis to LCMS. So putting a pricey column in there, is there a big increase in the cost of analysis at all?
No, we've actually, we're the one lab that has implemented it, obviously. And no, the analytical column probably costs £450, but it lasts for a long time. And I would also argue that the method is more robust for it, so it likely minimises downtime.
Right, that's a good news story in amongst this, that moving to at least getting rid of those analytical errors is at a no cost. So maybe that's why you're getting good adoption of the new method by a lot of labs.
Yeah. So I didn't mention this in the talk, but actually the study that we did with LGC, looking at the Capitana device and the newborn screening card, that was funded by the Specialist Commissioner for Metabolic Services. So I think that we felt that was a really positive signal at the time.
Yeah. So, I mean, are there mechanisms within the Association of Laboratory Medicine or elsewhere that can easily spread best practice, best methods across the labs in the NHS and elsewhere?
Yeah, I think so. Certainly in metabolic, we're lucky because we're a much smaller group of laboratories. So there's 16 or 17 in the UK, depending on how you count. And we have our own network, and we do talk to each other quite frequently. And again, the Association for Laboratory Medicine has got a very strong network. So I feel that there's ample opportunities to share best practice.
Okay. So it looks like we've not got any further questions, Rachel. Great discussion there. Just before everyone disappears, just like to go through a couple of slides myself. So there's some references there. I'll just leave that up for a moment so that people, when they watch it back, can take a look at that. And I don't know whether there's anything you want me to leave up there at all, Rachel. No,
that was just a spare slide in case I had time left.
Okay. Okay. So just for those of you online that aren't aware of the Patient-Centric Sampling Interest Group, we are a not-for-profit organisation looking to just understand what the challenges are within implementation of patient-centric sampling and microsampling approaches, and then figuring out how we can talk to each other and overcome these challenges. If you want to learn more, the QR code on the left, you can get to our website. The QR code on the right takes to the LinkedIn group where you can ask questions, share information, etc., or just write to us at contact@pcsig.org. Just upcoming webinars, we have one webinar a month other than in August. And so we've got May the 13th, we're coming up with analytical mass spectrometry workflow for VAMS and its application in cardiology and beyond with Jenny Van Eyck. And then in June, we've got remote monitoring of anti-seizure medications at home to microsampling devices in epilepsy with Chiara Cancellerini, and I apologize for the pronunciation of your name there, Chiara. So please sign up for those. They're all open for registration through our website at the moment, and we'll be talking about them a lot on our LinkedIn site. And again, I'd just like to thank our partners and our sponsors who make all of this possible. And I'd like to thank all of you for attending today. Really great conversation. And most importantly, I'd like to thank you, Rachel, for giving a really engaging story. I think it's a great story, and hopefully we're getting towards a happy ending with it as well. So, you know, it's not just a fairy tale, it's real. So thank you, everyone, and see you next month.
Thanks, Neil.